Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another review session, and this one is quite special because this is the last one for the year for any quizzes. Basically, this is the last quiz we're going to be doing, inshallah, on Tuesday, and it's going to be a chapter quiz. Yeah, inshallah, this will be another good review session. Make sure you have your calculator ready. Make sure you do the problems with me. Try and pause the video, solve the problem yourself, and then observe the solution. Okay? Let's go. Bismillah ar-Rahman ar-Rahim. Okay, so as I just said, please pause the video and attempt to do the questions before observing the solution. You will not be given the formulas in the quiz, so please make sure that you remember those formulas. And there's not many formulas that you have to remember. You just have to know that momentum equals mass times velocity. Let me just write some of those formulas right now. So the formulas you will need for the test are momentum equals mass times velocity. You definitely need to know that one. You also need to know that change in momentum or impulse is equal to force times change in time. Okay, those are the two main ones that you need to know, really. Can I think of any others that you need to know at this stage? Probably not. And just know that change in momentum equals P final minus P initial, or final momentum minus initial momentum. So really there's not much there for you to remember. Okay, should be easy, inshallah. Just make sure you have your paper and your pen ready, as well as your calculator. Let's do some study. Okay, so what is momentum? Momentum is a vector quantity. That's the first thing I want to start with. It's a vector quantity, which means it is an arrow with a magnitude. It has a size and it has a direction. So it has a size and direction. And the word size can also be referred to as magnitude. So if you see the magnitude of the momentum, it just means the size of the momentum. Okay? And it has a direction, so it can be north, south, east, or west. Okay? It also means that you can add them together because it is a vector quantity. So let's say, for example, there's a ball traveling over here, and it's traveling at 2 meters per second, and it has a mass, a certain mass of some sort. So let's say 1 kilogram, and it hits another ball that is traveling at 1 meter per second, and it also has a mass. What this means is once we work out the momentums, which is mass times velocity, so momentum is equal to mass multiplied by velocity, we can actually add those two vector components together. So in this case, the momentum is going to be 2 kilogram dot meters per second. And I hope that's obvious why that's the unit for momentum, because remember, it's mass times velocity. So it's m times v. What's the unit for mass? Kilograms. What's the unit for velocity? Meters per second. So in fact, that is the unit for momentum. So what's going to be the solution for this one? I hope you've had enough time to work it out. Half of 1 is, in this case, it's going to be 0.5 kilograms dot meters per second. And so what I can do now, since they are facing the same way, I can add them together and say the total momentum is going to be equal to 2.5 kilograms dot meters per second. What if they weren't facing the same way? What if one of them is going that way while the other one's going that way? Then what can I do? I can still add them together, except now, remember, it's a vector quantity, which means it has a direction. Now it's a negative. So it will be a total momentum of 1.5 meters per second. Oh, sorry, not meters per second, kilograms dot meters per second. Okay, I hope that makes sense. Let's move on. What factors influence momentum? So we kind of answered this already. The factors that influence momentum are the ones inside the formula. So momentum is equal to mass times velocity. That means I'm not worried about energy. I'm not worried about acceleration. I'm not worried about anything else. I'm just worried about the mass and the velocity. Those are the factors that influence momentum. Okay? Um, force and time can influence impulse, which is a change in momentum, but we will not worry about that. Directly speaking, it's mass and velocity. So here's an example of a problem that can show up on Tuesday. Let's see if we can solve it. We have a 2,000 kilogram car, and this is the mass, which has a momentum of 6,000 kilograms dot meters per second. So this is the momentum. How fast is it moving? So once again, we can actually put it in triangle form. Momentum equals mass times velocity. And so we have the momentum, we have the mass, so we need the velocity, and the velocity is going to equal to P over M, which is going to equal 6,000 divided by the mass of the car, which is 2,000, and therefore the velocity is going to be 3 meters per second, and whatever that direction is going to be, so in the positive direction. What is the conservation of momentum? So that is just a fancy word for saying that momentum is the same before and after. So conservation of momentum just means momentum before the collision equals momentum after the collision. So once again, a really useful rule when calculating velocity or when calculating mass and such. And we're going to come to find out how that is helpful. With every single collision, momentum is conserved. So there are different types of collision, and I want you to know that it doesn't matter what the type of collision is, whether it's elastic, whether it's inelastic, whether it's perfectly inelastic. With all types of collisions, momentum is always conserved. However, that's not the case for energy, for example. We're not learning about energy conservation just yet, but in terms of kinetic energy, that's the energy for movement. So if the object is no longer moving, or if the movement is different before the collision and after the collision, then it means it's not conserved, it's not the same. The momentum will be the same, but the energy might be different. But that doesn't matter because we're not worried about energy anyway. So as far as you're concerned, momentum is always the same before the collision and after the collision, and that's called the conservation of momentum. Here's an interesting question. A car and a bike, which one has the bigger momentum? Can we even solve it? Is it missing anything? And the answer is, of course, it's missing something. Just a second, I've just realized that I made a mistake here. It says 4.1. It's not 4.1, that was for grade 8. Just give me a second. I'll solve it using magic. Okay, hopefully that magic trick worked. So anyway, so we are obviously unable to solve this because it's missing some information. What is the information that is missing? Although we can probably tell that the car is bigger than the bike. So here's a bicycle, for example. I'm assuming we're talking about bicycles. So here's a bicycle, and obviously the bicycle is always going to be lighter than a car, generally speaking, at least. Okay, so here's a bike, and we have a car. So the car is going to weigh much heavier, have a much bigger mass than the bicycle. But what we don't know is the velocity. Now, why is that important? Now, somebody might say, well, hang on, it's not really that important, right? Well, no, it is, because what if the car's not moving? What if the car has a velocity of 0 and a mass of 1,500? Now, the bike might only have a mass of 50 kilograms, okay, but a velocity of 10 meters per second. Then automatically the momentum of the bike is going to be 500, while the momentum of the car is always going to be 0, because 0 times anything is 0. So can we even solve it not without the velocity? We need both velocity and mass. Okay, so just remember that. However, if the question says, for example, a bicycle that is moving at 100 meters per second, which is impossible, and a car that's moving at 1 meters per second, then that's when you do your calculations and you multiply the mass and the velocity and you can work out which one has the bigger momentum. Okay? What is impulse? Impulse, simply speaking, is change in momentum. So that's momentum before, momentum after minus momentum before. So change in momentum equals impulse. And it looks like this, change in momentum. That's what the triangle means, change in. How can you reduce the force during a car crash? Okay. So impulse turns out has a formula. It's not just momentum before and momentum after, or momentum after minus momentum before. Impulse also has a formula, and the formula for impulse is equal to force multiplied by the change in time. Force multiplied by the change in time. And that's quite useful because that's something that obviously scientists have been using to increase the survivability of people in car crashes and such. How? As you can see here from the formula, if we have a force acting on a car, let's say for example a car is moving and it has a mass and it crashes into a wall. Here's a wall and it crashes into a wall. Now that force is there. So let's say 5,000 newtons. That force is reliant on the acceleration of the car or deceleration of the car, as well as the mass of the car. So that's not something I have a lot of control over. The person is going to go at a certain speed and they're going to go at a certain mass. But what I might have control over is impulse, that change in momentum, right? And if I can have it so that the change in momentum is twice as long, then the force experienced by the driver is going to be half. So even though the impulse is going to be the same, the change in momentum is going to be the same before and after. If I make it so that the time is twice as long, then the force will be half of what would have happened had the time been in its original state. I feel like I've said so much and I've confused people. So let me do the maths and show you what that looks like. So that this car here, for example, has a mass of 1,000 kilograms and has a speed of 20 meters per second. So that is velocity and that's mass. Okay, now pay attention. The momentum is going to be 20,000 kilograms dot meters per second. That's obvious, I think. And the momentum after is going to be zero because the final velocity is going to be zero. So the change in momentum or impulse is going to be equal to 20,000. Okay, now let's say that is the change in momentum, or that is impulse, 20,000 kilograms dot meters per second. Now that's going to be equal to the force multiplied by the time. Let's say the time of the crash was 1 second. Let's say the time for the crash was 1 second. That means the car crashed into the wall and it took 1 second for it to stop completely. That means the force of the crash is equivalent to F times 1, which is 20,000 newtons. So in this case, F will be equal to the 20,000 newtons, which is the same as the impulse. Now that is catastrophic. That is a big force, okay? So to put that in perspective, if you're a driver and you're experiencing that kind of force, it's like experiencing 2,000 kilograms on your chest, okay? Which is deadly. Now what's going to happen if the impulse stays the same? We can't do much about the impulse because impulse has to do with as I said, the mass and the velocity, which is the change in momentum. Let's keep the impulse the same, but this time we've slowed it down so that the change in momentum takes 3 seconds, okay, or 4 seconds. So we've got airbags, we've got crumble zone, we've got things that are going to absorb that crash, so it's going to slow it down a bit. So let's say instead of 1 second, now the time is 4 seconds. So that means suddenly the force is going to be 1/4 of what it was. It's going to be 5,000 newtons. And 5,000 newtons is about 500 kilograms. Now that is still quite high, but it might actually be survivable compared to 2,000 kilograms, or the feeling of 2,000 kilograms. And so this is very, very important. Decreasing or increasing the time can decrease the force experienced by the person or the passengers. Simple as that, okay? So what happens to the impulse if we double the time or halve the time? The impulse remains the same. I want you to know that. The impulse remains the same because that's a change in momentum. But what changes the force? Okay? So the impulse, which is the change in momentum, that remains the same. If a car that is 2,000 kilograms and that is moving at 2 meters per second hits a wall, the change in momentum is going to be 4,000. There's nothing much anyone can do about it. The impulse or the change in momentum is going to be the same. So what's going to change is the force, because the force experienced has to do, the force and the time are related to each other. So the force times time equals impulse. So even though we can't change the impulse, we can change the force by increasing the time. Okay? By decreasing the time of impact, we can increase the force. And so now, I want you to think about this. If I'm kicking a ball, should I kick a ball? If I want to kick it with such a high force, do I decrease the time of contact between my foot and the ball, or do I increase the time of contact between my foot and the ball? And hopefully, let's just think about it for a second. I want to increase the force experienced by the ball. Now, the ball has a mass, and my kick has a certain force depending on how much force I'm applying, but it's also dependent on the time I'm applying. So if I give it a quick kick, then it's going to increase the force. Now, the change in momentum for the ball might remain constant, but if I decide that I'm going to kick it very quickly, just like small time of contact. Small time of contact. So I'm kicking it and it leaves my hand immediately, or it leaves my foot immediately. Then that's going to increase the force. It's going to increase the force experienced by the ball. Okay? If I want to make the force smaller, then I can have that contact time much longer. Okay, so if the contact time is longer between my foot and the ball, then the force is going to be smaller. The impulse doesn't change. The change in momentum is more or less the same. Do you get what I mean? So, yeah, because that's mass times velocity. Before and after, that's going to be the same. But the force and the time are different. Okay? Let's look at the third example over here. So both of those examples, so the second one, what happens to the impulse if we double, what happens to the impulse if we double the time, or we halve the time? Nothing. The impulse will remain the same. What happens to the force if we double the time? If we double the time, the force will be halved, so we'll have half the force, and if we halve the time, we'll have double the force. Okay. A force of 50 newtons acts on a ball for 2 seconds. What is the magnitude of the impulse? Well, hopefully by now you're familiar with this formula. The impulse, or the change in momentum, is equal to the force multiplied by the change in time. Okay, so what happens to the impulse? We've got the force, which is 50 newtons, and we've got the time, which is 2 seconds, and so the impulse is going to be 100 kilograms dot meters per second, or if you want, you don't have to use the units for momentum. You can use the units for force and time. So you can write 100 newtons dot seconds. Both of these are correct. Okay. What are the different types of collisions? So we have three different types of collisions. We have an inelastic collision, or a perfectly inelastic collision, or a completely elastic collision. So three different types. Elastic, well, actually two. So elastic and inelastic, which means one is where the objects bounce off each other, and one where the objects don't bounce each other and they stick together. But in terms of inelastic, there is a normal inelastic and there is a perfectly inelastic. So regular and perfect. Oh, perfect. And what that has to do with the energy, and we're not concerned with the energy at the moment. So all you have to worry about is, in terms of momentum, whether it's elastic, regular inelastic, or perfectly inelastic, all three of which have conservation of momentum. So that means momentum before equals the momentum after. And we will be primarily concerned with this guy here. So for grade 11, what we're concerned with is perfectly inelastic collisions, which means the objects stick together and there's no loss whatsoever in momentum. The momentum is conserved, and yeah, so they stick together and move together. Here's an example of a problem that you could face as well. So a baseball batter changes the velocity of a ball thrown at them from 7.5 meters per second to negative 5.5 meters per second along the same axis. What does that mean? 7.5 to negative 5.5. What happened to the velocity? So what happened to the velocity in this case, as some of you might have guessed, is that it changed directions. Okay, so the ball must have come this way and it was traveling at 7.5, and then this man here has hit it and now it's traveling at 5.5 in the other direction. Okay, along the same axis. If the impulse delivered is minus 6.5 kilograms per meters per second, calculate the mass of the baseball. Okay. So the first thing we need to realize is that we can actually work out the change in momentum or the change in velocity. And once we have the change in velocity, and we have the impulse, which is change in momentum, we can work out the mass of the ball. So we can actually use both of those formulas in the moment. So momentum equals mass times velocity. And we know that change in momentum is equal to force times change in time, or final momentum minus initial momentum. So how does that help us? Let's have a look. We have change in momentum equal P final minus P initial, or the final momentum minus the initial momentum. But we also know that PF equals M times velocity final. That's what the final momentum equals, minus mass times velocity initial. Remember, the mass hasn't changed. So with that in mind, we can see that we can rearrange this formula and it will give us mass times Vf minus Vi, and that equals change in momentum. So we can use this formula here. So this is how I worked it out. So impulse or change in momentum is equal to P final minus P initial. P final minus P initial. That's the first one. Then I realized that, hang on, P final is mass times final velocity, while P initial is mass times initial velocity. And of course, I can rearrange this and make it so that since m is the same for both, mass times final velocity minus initial velocity. And so now I can do this. I can say, well, I've got this formula, mass times Vf minus Vi. And I know that the impulse is equal to minus 6.5. I don't know what the mass is, but I know that the V final is going to be negative 5.5, while the V initial is 7.5. So I can work with this. I can go m, or the mass, is equal to negative 6.5 over negative 5.5 minus 7.5. And so the mass is equal to 0.5 kilograms. That's the answer. Okay, so I just did that in a long, windy way, but if you know what you're doing, all you have to do is go, okay, so the final velocity minus the initial velocity multiplied by mass equals the change in momentum. So this over the change in velocity is going to give me the mass. Okay, let's have a look at this problem over here. A golfer hits a 0.2 kilogram ball with a force of 74 newtons. So this time we've got the force. The speed of the ball after being hit is 1.5 meters per second. So we've got the mass, we've got the force, as well as the velocity. And we would like to know the time. So I can work out the momentum. Well, the momentum before is going to be 0 because the ball is just sitting on the grass and then the golfer hits it. So therefore, the change in momentum is equal to momentum after. Because the momentum before is 0, so the momentum after is going to be mass times velocity. So final momentum, P final, is going to be mass times velocity, which equals to 0.2 multiplied by 1.5, which is equal to 0.3 kilograms meters per second. So that's the change in momentum essentially. That's final momentum as well as change in momentum because it's P initial equals 0. So it's just the same, 0.3. So now that I know that change in momentum is equal to 0.3 because that's the final minus the initial, and I know that the force equals 74 newtons, I can work out what the time is going to be because remember my other formula, change in momentum equals force multiplied by change in time. So it's going to be 0.3 is equal to 74 multiplied by the time. And so the time is going to be equal to 0.3 divided by 74. And that is 4.1 times 10 to the power of negative 3 seconds. Or 0.004 seconds, which is a very short time. Now, that's expected. Of course, the club is going to be in contact with the ball for a very short time. Okay? But what is that going to do to the force? If somebody's been paying attention, they should know that since the time of contact is very, very short, the force is going to be really high, which is expected once again. Because if the force is quite high, that means the ball is going to travel really far. It's going to have huge acceleration because force is equal to mass times acceleration. Force is equal to ma, mass times acceleration. So if the contact time is less, the force is going to be more. And if the force is more, then the acceleration is more. So if I'm a sports person and I'm trying to kick a ball, I want the contact time to be short so that the force is going to be higher and the acceleration is going to be more. Or if I'm a volleyball person and I'm trying to spike a ball, I want the contact time to be short, like a slap, like a quick, just boom, like a quick slap. Or if I'm a boxer, for example, it's going to be a quick punch, a quick punch. I'm not going to go and like I don't want to roll the punch and actually have as much contact as possible. It's going to be quick because that delivers the highest amount of force. Just physics, okay? The highest amount of force means the highest amount of acceleration. If I want to reduce the amount of force, I want to roll with the punch. So if somebody's punching me, for example, I'm not the boxer, I'm not the one person punching, but I'm the one getting punched. What I want to do is I want to roll with the punch, okay? I'm not going to stay there. I'm going to roll with it because that reduces the amount, sorry, that increases the time, which reduces the force. As long as you increase the time, you reduce the force. If you decrease the time, you increase the force. Okay, moving on. A 35 kilogram boy is standing on a frictionless icy surface when his 12 kilogram dog, so here's the boy, and he's standing on a frictionless icy surface when his dog jumps on him. Okay? And the dog has a mass of 12 kilograms while the boy has a mass of 35 kilograms. The boy is stationary, which means he's not moving, but the dog is traveling at 6 meters per second. And then it says calculate the speed of the boy and the dog together after the collision. So here's where the conservation of momentum comes into play. Remember, momentum before equals momentum after. What was the momentum of the boy standing by himself before? 0, because momentum is equal to mass times velocity. If he's not moving, then his momentum is 0. So the only thing that has momentum is the dog. The dog was running. The dog's momentum is P of dog. Momentum of the dog is equal to mass times velocity, 12 times 6, which is equal to 72 kilograms dot meters per second. Okay? Now that is going to be the total momentum after. So that's going to be, even though that was the initial momentum for the dog alone, because the boy didn't have a momentum. So the total momentum before was 72. Because the dog and the boy equals 72. The boy wasn't even moving, it was 0. So it was 72. After, it's also going to be 72. So we know that the momentum of the boy and the dog combined, that means 35 plus 12, so 47, times a certain velocity is going to equal 72. Now they're asking us for the speed, okay? Do we know the mass after? Yes, the total mass is going to be equal to the boy and the dog, which is 47 kilograms. Do we know the momentum after, or the total momentum? Yes, we do, because it's the same as before, which is 72. So can we work out the velocity? Of course, sure. Remember, momentum is equal to mass times velocity. So it's 72 divided by 47, and so therefore the velocity is going to be 1.5 meters per second. Simply speaking, it's going to be 72, which is the total momentum, divided by 47, which is the total mass of the dog and the boy moving together. And it's 1.5 meters per second. Now, it's worth mentioning at this stage, where is it moving? It's moving in the same direction as the dog was moving before. The same direction as the boy. So the dog. The dog was moving at 6 meters per second that way. Then they are both now moving back at 1.5 meters per second. Okay? Let's move on. Oh, that's a different question now. A 35 kilogram boy is standing on a frictionless icy surface when his brother throws a backpack at him. So this same boy now, he loves ice skating. He keeps going to the ice skating rink. And this time his brother throws a backpack at him. Okay. Hopefully that resembles a backpack. And the backpack has a mass of 4 kilograms. 4 kilograms. So it's very similar to the dog example. And they both move backwards. at 0.2 meters per second. So this time it's slightly different. We have the velocity after, we have the mass of the boy, the mass of the backpack, and we have the velocity afterwards, which means we have the momentum after, not before. We have the momentum after, and what is it asking for? It's asking for the initial speed of the bag. So how fast was it moving when the boy received the bag? How fast did the brother throw the bag at his other brother, or at the boy? Once again, what do we need to do? We need to work out the total momentum before and the total momentum after. We don't have the total momentum before. We have the total momentum after. But lucky for us, the total momentum after is equal to the total momentum before. What is the total mass? The total mass is mass total is equal to 4 kilograms plus 35, which is 39 kilos. Okay, what else do we have? We've got the momentum after. How? Momentum after is equal to mass times velocity. We have the velocity, 0.2, and we have the mass, 39. 39 times 0.2 equals 7.8. So we know that the momentum is 7.8. Okay. And the velocity, of course, after is 0.2. What we're trying to work out is the velocity of the bag. Do we have the momentum? Yes. There. And it's the same before and after, because the boy wasn't moving. So we know that momentum now is 7.8. The velocity is what we're trying to find out. So let's just use the formula. Easy. Momentum equals mass times velocity. We have 7.8 divided by 4, which is 1.95. So the velocity equals 1.95 meters per second, which is quite fast. So he threw the bag with a speed of 1.95 meters per second. The boy caught the bag and he moved back with a speed of 0.2 meters per second. Okay, let's move on. We've got a car. The car has a mass of 2,400 kilograms and the speed of 16 meters per second. And it crashes into a truck. And the truck has a mass of, well, we don't know. We don't know the mass of the truck. But what we know is that both of them together afterwards were moving with a speed of 7 meters per second. So what we're trying to work out is the mass of the truck. And it's very easy. Remember, momentum before equals momentum after. Now, lucky for us, this thing here, the truck wasn't moving. It was stationary. It was parked. So what that means is the total momentum of the system before is equal to the momentum of the car, which is 2,400 times 16. So the total momentum before, P initial, is equal to 2,400 times 16, which is 38,400. And so it's going to be the same after, right? Do we know the total mass after? We don't know the total mass after. But we know the speed. We know the speed after. So we can work it out because it's mass times velocity. We have this, we have this, we can work out the mass. But there's one more step, because if we work out the mass, it's going to be the mass of the car and the truck combined together, right? So let's work out the mass anyway. So it's 38,400 divided by 7. So the total mass, it tells me the mass is equal to 5,486 kilograms. But remember, that is the mass of the car and the truck after they've stuck together. So I still have to do one more step, which is subtract 2,400, which is the mass of the car. So minus 2,400, and then I come to the mass of the truck, which is 3,086. But since I'm working with two significant figures, I'm going to say the mass of the truck is going to be 5486 minus 2400, which is approximately 3000 kilograms. Approximately 3000 kilograms. 3086, but 3000 kilograms is fine. Okay, so the main thing with this kind of problem, the steps are as follows. Make sure you always have at least the momentum before or the momentum after. If it's asking for something before, like what was the speed before, it means you have the momentum after. If it's asking for the speed after, it means you have the momentum before. But it doesn't matter, because remember, the momentum before equals the momentum after. Once you have one, you can solve for the other. Okay? It's as easy as that. Okay? Let's go to the next one and see if we can solve it. A boy and his father are on a skating rink. Once again, why are we using icy skating rink? Because we're trying to ignore all sorts of friction. Okay? They stand in the middle as the boy applies a force of 50 newtons on his father. The boy applies a force of 50 newtons on his father. Okay? So of course, this here has to do with Newton's laws. This lasts for 2 seconds. So we've got the time, which is a big clue that we're dealing with impulse. We've got the force. And it says here, calculate the momentum of the boy and the father after the push. Okay. So basically, what you need to understand is that before the push, excuse me just a second. Before the push, the momentum was 0, because the boy and the father were not moving, they were standing. So we only have final momentum here. Change in momentum is equal to the final momentum, which is going to equal, change in momentum is equal to force multiplied by change in time. Do we have the force? Yes, we do. 50 newtons. Do we have the time? Of course we do. We have 2 seconds. So the change in momentum is equal to be 100 kilograms dot meters per second, or in this case 100 newtons seconds. Okay, so that's going to be the impulse, or that's going to be the momentum of the boy, right? But turns out it's the same for both, because for every action there's an equal and opposite reaction. And so basically the sum of the two momentums is going to be 0. And so if we have a momentum of 100 this way, then the momentum of the father is going to be negative 100 this way. Simple as that. Okay? So if you get a question like this, all you have to do is remember that this is the force, that's the time. So once I work out the momentum, or the change in momentum, then it's going to be it's going to be positive for one and negative for the other. Okay? That's all you have to remember here. It's going to multiply the force by the time, which gives you the impulse, or the change in momentum, which is actually the momentum, because the initial momentum is 0. So it's going to be the same for both the father and the boy afterwards. Okay? And since there are no external forces acting on it, they actually cancel each other out. Okay, which is what we expect. Let's keep moving. I think this might be the last question here. The boy, 30 kilograms, and his father, 80 kilograms, while skating on ice rink, decide to charge at each other. So they decide to do this big Hollywood thing where they charge at each other and they hug each other in a perfectly inelastic collision. Okay, so they become stuck together as they hug each other. The boy is traveling to the right. Here's the boy traveling to the right at 3 meters per second, 3 meters per second, and he has a mass of 30 kilograms. And the father, he is charging at him to the left at a speed of 2 meters per second, and he has a mass of 80 kilograms. Okay? And then it says what's going to happen to their velocity after they hug. So once they hug together, what's going to happen is they're going to form one mass of 110 kilograms. So what do we need to do here? We need to work out the velocity after. In order to work out the velocity after, we need to work out the momentum. The total momentum before and the total momentum after is going to be equal to the total momentum before. So what is the total momentum before? It's going to be 90 for the boy. How come, mister? Well, velocity and mass. So it's mass times velocity. So it's going to be 90 for the boy, and it's going to be 160 for the man. Except, you got to be careful with signs. One is going one way, the other one's going the other way. So I got to make sure that the signs are opposite. So if I have positive for the boy, I can have negative for the man or the father. Now, it doesn't have to be that way. It can be the other way around. It doesn't matter. It's all arbitrary. So anyway, I'm going to choose plus 90 for the boy, minus 160 for the man. So the total momentum before is going to be plus 90 plus negative 160. So you got to add these two together, which will give you 70 or negative 70. So the total momentum before, P initial is equal to negative 70. Okay, which means P final is equal to negative 70. So now I have the momentum after, and I have the mass, which is equal to 110 kilograms, and I can work out the velocity after. So the velocity after is going to be negative 70 divided by 110, which is equal to negative 0.6 meters. Does this result make sense? Of course it makes sense. The father is bigger, and the father has a bigger momentum, and the father is going to be, well, most likely, once the father hugs the boy, they're going to be moving towards the direction of the father. So this is what this is saying. What this is saying is that once they hug each other, they're going to be moving this way slightly at 0.6 meters per second. Which makes sense. Okay? That is all from me. I realized that it was quite a bit. Please go back through it again if you need to. That's good practice. It's a short video. It's only 50 minutes. We're used to so much more in physics. Okay, try and watch this again. And try to explain it to each other as well. So that's good practice. If you don't understand it, try and listen to it from someone else, from a classmate. Perhaps it'll help explain it better. And of course, I'm always available if you need me to explain anything to you. Please send me a message on Teams. I am always available. Thank you very much. Over and out. Take care. Assalamu alaikum.